I just graded the homework that you guys just turned in, and one student did what I asked. Everybody, everybody, I think, did at least one fairly close to what I was asking, but pretty much everybody kind of did their own thing. And what I would like to do today is just go over and be a little bit more explicit about what I'm looking for this algorithm. And again, I really want to bring this up. Like, when you learn how to do long division, your teacher forced you to do a bunch of stuff that you really didn't need to do. Like, for instance, if the question was this, we're going to take, how about 400 and divide it by 25. Now, you're clever, I'm clever. We can figure this out without doing the long division. Like, I think 400 divided by 25 immediately goes through my head is $4 divided by 25 cents, right? In other words, how many quarters are there in $4? And so, being a little bit clever here, I could think, well, 4 times, it should be 16, right? Like this $4, yeah, because, oh, that should be a 25. I think, well, if it's 100, there's 4 quarters and $1. So $1 is 4 quarters. There's $4 here. So 4 times 4 is 16. We're all clever and we could all figure that out, but that's not going to reinforce how to do an algorithm. And so in this case, you would just blindly, or basically, yeah, blindly just follow the algorithm. And you ask yourself, okay, is 25 bigger than 4? Or is 25 smaller than 4? No. Is 25 smaller than 40? Yes. How many times does 25 go into 40? Well, 1 time. And so you go 1 times 25. And then you subtract that off. And that gives me
15.
15. There we go. So 15. And then the algorithm says, okay, is 15 bigger than 25? No, so I have to drop a 0. And then I ask myself, okay, how many times does 25 go into 150? And then I could be a little clever and say, well, hold up. $1.50 has a total of 6 quarters in it. Yeah, because $1 would be 4, 50 cents would be 2 more quarters. So I say, okay, 6. And then I kind of check myself and go, let's just make sure 25 times 6 gives me 30 and a 3, 6 and 2 is 12, 13, 14, 15, 150. 0. My algorithm terminates, and so I could finally conclude that 400 divided by 25 is 16. But we knew that, right? There's a much better way of figuring this out. We didn't need to go through all that. But when you're learning long division, you do need to go through it. And like a lot of, and now I don't want to say like everybody was abysmal or anything like that. Like, you guys, it seems like you've got most of it right, but there are a few things we're going to address today that I noticed a lot of people did, and I want to clear those up. And so part of the algorithm that we're developing for getting a matrix into reduced row echelon form, there are certain steps that need to happen. The same way, like, all of this needs to happen. And yes, it's tedious. And yes, there is, in many cases, there's a much better way of doing it. But nonetheless, we need to go through these steps every single time. Again, that's the point. I'm trying to, right? Like, when you're learning how to, I don't know, shoot an arrow or something, right? You do it over and over and over again. And maybe once you get all that down, then your coach or whatever says, okay, now you could start to do this a little bit a different way. But for right now, this needs to be done this way every single time. And so that's what we're going to do. So, okay. All right. So let's just do a bunch of examples, and along the way, I'm going to point out some things that some people did, or rather, I'm going to point out what's important about each step and what I'm looking for each step. And so let's start with, this is from page 166, number 10. I'm going to write this right here. Page 166, number 10. Gives us a system. 6x minus 3y equals 18. And 6x plus 3y equals negative 12. Okay. So I'm going to get the steps written out right here so we don't forget. One is we're turning our system into a matrix. Everybody was very good at that. Everybody knocked that out of the park, which is not, and that's not like, I'm not just saying that, like, that's actually, believe it or not, that's the big conceptual jump right there. And people often have a rough time with that one. Everybody's knocking that out of the park, which is great. Step 2, get a leading one. Step 3, we get zeros under the leading one. Step 4, we get a new leading one, one down and one to the right. So and I'm just going to do that like this. One down and one to the right. Right? So to be clear here, we start getting our leading one here, and then we get zeros beneath. Then from our old leading one, we go down one and over one to the right, and that's where we want our new leading one. Then we need to get zeros beneath that. Oh, but this is just a 2 by 2, so we don't need to worry about that. But if it were bigger, we would just keep doing that and keep going down and over, getting leading ones as we go. But get a new leading one. We'll get to that when we do 3 by 3s. So, but right now, we get a new leading one. Then step 5 is we get zeros above the leading one. Above the new leading one. Once that's done, since this is a 2 by 2 system, if you have a leading one here and zeros beneath it, and then you have a leading one here and zeros above it, well, it turns out you're done. You've solved the system. We don't need to keep applying these steps over and over again, like we will with the 3 by 3 or bigger. And so in this case, once we get zeros above that, then all we're left with is ones. And so we can turn our matrix back into a system. And that is the goal. That is our goal. So now, before we begin, if you're clever, and I know each and every one of you are clever, because I've seen the clever stuff you do in your homework. And if you're clever, you could see this. Like, dude, I could just add these together. Like, if I add the top one to the bottom one, those y's go away. And you're absolutely right. This is just like with the long division thing. It's like I could just see that it's 16 quarters in $4. Like, I don't really need to do much work. The same way here, you could say, dude, this is much easier. I could just add those together. And when I add them together, I get 12 x's. All the y's disappear, and I have 6 whatevers. We might have done this one in class. Did we do this one in class? I don't know. Anyway, at any rate, and then we say, okay, since that's the case, we divide both sides by 12, and x is equal to 1/2, and then we can move on from there. Yeah, I get it. Like, a lot of times there's going to be a much easier way of doing these, but again, the goal, the whole point of doing this is to reinforce this. It's to learn this so that it becomes second nature, the same way long division at some point became second nature after you've done 1,000 different problems. So that's what we're doing right now. So step one, system into matrix. And so somebody tell me what the top row is.
6, -3, 18.
There we go.
And then the bottom is 6, 3, -12.
All right. Now, what do I have to do for step two?
Leading one.
And so how do I get that leading one?
Times by 1/6.
Times which one by 1/6?
Row 1.
Row 1 by 1/6. There we go. And so the 6 jumps through and we get 1. That was the whole point. -3/6 is -1/2. And 18 divided by 6. 3, right? Is that right?
Yes.
Yes.
I think I mentioned in class, like Josh and I, we both were messing up this problem. He messed up a problem, and I was like, "Where did he mess up?" I could not find out why, and it was because he did 18 divided by 3 = 9, and I was like, "Yeah, right, of course." And yeah. So anyway, okay. Now here's the thing: this row down here does not change. We're keeping that row exactly the same. Okay. So after step 2, this thing has to be a 1. And here's the thing. This is the thing. I'm going to write this in red. This, once you have a leading 1, it will not change. That is, for every step that we do thereafter, no matter how many steps it takes, every single time that 1 is going to stay a 1. There will never be a point where in my next matrix, now I'm going to write it as 2, -1, 6, or 6, -3, 18, or something like that. This has to stay 1. And we want it to. So now, okay, so we got our leading 1. Now we have to get 0.
How does it stay 1?
Because we're not going to change it. The only way that this is going to change is if I then multiply it by something, which we're not going to do. So again, you could be clever and you could say, hey, hold up. Now, wait, let's do one more step. Let's do one more step so we could, because maybe you're saying something that I'm not saying. So the next step, right, to get zeros under the leading 1, we need, right, the whole idea is I'm going to multiply this by something and add whatever the result is to this. And so I'm going to add something to 6 to make it a 0. What does it have to be?
-6.
-6. How do I multiply this row by something in order to turn that?
-6.
It has to be -6, right? This is the nice thing about this algorithm is there's a lot, you don't have to do much brain work at this point. And so here, maybe this is what you're saying. It's going to change, like, because we're changing it right now, but we're not actually going to rewrite that row that way. We're going to keep that row because what we're doing, here, I'm going to go ahead and do it. The -6 jumps through. The -6 hits the -1/2. We get -6 over -2 is +3. -6 times 3 is -18. And then we're going to add, right? So this is all kind of one step right here. We're taking -6 times row 1 and adding it to row 2. But the thing is, we are not changing row 1. Row 1 has a leading 1. So we're keeping it like this. It is not changing. And so that's what I mean by the leading 1 is not going to change. And yes, we had to multiply it by something to get something new, but the system, the matrix that we're bringing along for the ride, this new matrix is going to have a leading 1 here the whole time. We are not changing that at all. And so what does change here is the -6 and the 6 give me a 0 as desired. That was the whole point of doing the -6 thing in the first place. The 3 and the 3 come together to give me a what?
6 and then -30.
-30. Now, one more thing. You could just, you're clever, I know. You could say, wait a second, like, look at all that work that you did when you could have just looked at the very beginning and said, just subtract that from that. Like from the very beginning, you could get a 0 right there by taking that bottom equation and just subtracting off the top equation, -6x plus 3y or whatever. Whoa, that's why. And then subtracting that guy off, right? And saying -18. I get that. That's just like the quarters, right? $4 is 16 quarters. I get it. You get it. We all get it. We all know there's a much easier way of doing it, but that's not what this is about, right? This is about drilling this algorithm so that it's just second nature, that you could just do it in your sleep. Like, that's the point. And I'm sorry, but that's the point of all of this. And so, yes, there is a better way. There's a much easier way of doing it. But the point of this is to drill this algorithm. And so, okay, let's think about this. We did our system to matrix. We got our leading one. We got zeros beneath that leading one. We are done with getting zeros. So now we need to get a new leading one that is down
Times by 1/6.
1 unit. And so the way to do that is to simply multiply this entire row by 1/6. Now I'm going to rewrite this up here. And remember that I haven't been saying this, but every single time we go from one matrix to another matrix, one of those rows is not changing. So if you'll notice, when we went from our original system to our second one, this row stayed exactly the same. When we went from this one to this row stayed exactly the same. When we go from this one to this one, it's again, the top row is not changing. 1 minus ½ and 3. Now, the bottom row is the only one we're changing. And Joe, you told me we're multiplying through by -1 or by +1/6. And so the 0 stays a 0. The 6 and the 6 give me a 1, which is what I wanted. And then what is -30/6?
5, -5.
-5. There we go. Okay. Now, again, the same comment applies. This leading one is not going to change. There will be no point at anything that I do hereafter is that one going to turn into a 1/2 or a 7 or anything else. Once you have a leading one, this is a leading one, then every matrix that comes after it, that leading one is going to stay in place. And yes, we're about to manipulate this thing and multiply by this row by something, but I'm not going to replace that in the matrix itself. So, okay, we got our new leading one. That was step 4. Now, step 5, we need to get
5 times the bottom row by 1/2 and plus it to the top row. And
yes,
in the place of the top row.
There you go. There you go. And why? This is my reasoning, right? Is like, I need to add something to -1/2. So again, the reasoning is trying to get a 0 above that. The only way to add something to 1/2 to make it into 0 is +1/2. And so, because I have that leading one, it's mindless. I don't need to really use my brain here. I can just say, well, whatever the opposite of that number is, which is that's what I'm going to multiply that through. 0, +1 times +1/2 is 1/2. -5, and that makes -5/2. And now I'm going to add that to there. Let's see what we get. Okay, again, one of these rows is not changing. This row is the thing that I just operated on. It is not changing. And now you'll notice, like, you might say, well, hold on, you told me that the leading one, the leading one's not going to change, and now we're changing that top row. Yeah, but because we got zeros beneath the leading one, when we go to add these guys together, that leading one is not going to change. And that's part of the beauty of this algorithm, is that you first get a leading one, then get zeros beneath it. Then anything you do with the other ones, adding it to the top one, well, it's always going to have a zero right there. And so when we bring that back up, like we're doing right now, we're taking half of this and adding it to that one to get that. And then whatever 3 and minus 5 halves is, like that leading one is still not changing. That leading one is staying a leading one. And so 3 minus 5 halves is the same thing as 6 halves minus 5 halves. That sounds right. Yeah, 6 halves is 3. So 6 halves minus 5 halves is 1 half. Yeah. I have my zeros above my new leading one. And in this case, the algorithm terminates. And this is exactly what we're looking for. This means that x plus 0 y's is equal to 1 half. So x equals 1 half. 0 x's plus 1 y equals -5. We took our matrix back into a system and we are done. So, questions on that? Okay. Let's do one from your homework last time, because there was this. Was it this one? I think it was
Are you gonna have us do a makeup for the last one?
Yeah. And it's 7 problems, so it's not that bad. And it's really good practice to just do these over and over and over again, which I know is a huge pain, but it's yeah. So let's do this one. So okay, I'm leaving this up. Can I get rid of all this stuff?
Yes.
It was this one, yeah. So this is from page 161. Number 11. This was this. I think everybody might need to make this up, I think. So we could translate this system into 1/3 x plus y equals -1 plus y equals -1. And then 4x minus 3y equals 18. Okay, so following the algorithm. And great thing about an algorithm is we rarely need to use our brains. Unless it's like adding fractions, then we have to use a little bit of brain power. But for the most part, each one of these is just cut and dry. So the system to the matrix. Excuse me. Let's go ahead and look at that. Okay, so what's row number 1?
1/3, 1, -1.
1, -1. Yes. Second row.
4, -3, 18.
18. Perfect. Now, okay, we've done step 1. Step 2, get a leading one. How do I do that?
Times by 3, the top row.
Multiply the top row by 3. Okay, so I'm going to do that. Now, I'm changing the top row, so that means I'm not changing that bottom row. So I'm going to go ahead and write the bottom row first. It's not necessary, but it could help. So we're multiplying that through by 3. So that gives me 1, 3, -3. Now, that leading one is not going to change. Every single one of matrix that I'm going to write afterwards is going to have a 1 in that position right there. Okay, so we're done with that one. Now we need to get
The next step would to be times the top one by negative 1/4, and then minus it from the bottom.
Mm,
If I multiply the
Negative
top by negative 1/4, then I get negative 1/4 minus 3/4 plus 3/4.
-4.
Is that gonna?
-4.
Yeah, yeah. All right. And you'll notice that with each successive step on one of them, you're going to be thinking, ooh, it's 1 over that amount. And then on the next one, you're going to be thinking, oh, it is that amount that I need to multiply by. And so, yeah, -4 times the top one. And I'm going to go ahead and write it just below here. And so that gives me -4. 3 times -4 is -12. -3 times -4 is +12. And then I add those to that. The top row is not changing in this case, so I'm going to write it first. Now, 4 -4 give me a 0, which is the whole point. That's why I did that in the first place. -12, -3, 12, 15, minus 15? Minus 15? And then 12 and 18, 8, 9, 10. So 0, carry the 1 gives me a 30. This is getting a little crammed. I skipped too much right here. I'm just gonna rewrite this up here. This is the same room, just to give myself room. 1, 3, -3. 0, minus 15, +30. Okay, so we got zeros under the leading one. And again, if we had a bunch of rows, which we're going to have with a 3x3 or a 4x4, we just keep doing that until all we have are zeros down there. And now we move to our next
Times the bottom by -1/15.
There we go. 1 over -15. And so we do that. We get from the top 1, 3, -3 is the one that is not changing. All right, let's have a little bit more room here. 1, 3, -3 is not changing. Now multiplying that guy through 0. -15 over 15 is 1, which is exactly what we wanted to happen. And then we have 30 over -15. What's that?
-2.
-2. Did I get those right? That's supposed to be positive. Yeah, okay. So -2. There we go. -2. Now we're done. We got our leading one. So now we need to get zeros above the leading one.
So multiply the bottom by -3.
And plus it to the top.
And plus it to the top. Okay. And so, and you'll notice the way I like to do this each time I'm doing this is I just write the thing that we're about to add above the one or below the one that I'm about to add it to. Like, that's just a convention. That's something that I developed over, however many years of doing this. Is like, I'm really trying to keep myself honest here. It's super easy to mess one of these up. And so, and you'll notice if you mess one up, like even at the very beginning, if you switch a sign, like the rest of everything is you're done. Like you're gonna have to write, if you mess up one sign at the very beginning, you're gonna have to write 1, 2, 3, 4, 5 matrices all over again. So it pays to just be a little extra careful here during these steps. And that's why I like to write these out. So although I'm not demanding that, that's not part of the algorithm. I'm not going to be grading on that. It's just, this is how I've kept myself honest. And by honest, I mean like end up at the right answer and like trying to prevent mistakes as much as possible. I found that this works really well. So, okay. 0 and 1, I combine them and get a 1. This and this, of course, give me a 0. That's why I chose to multiply by -3 in the first place. Otherwise, I would have chosen a different number, right? So, of course, that gives me a 0. Finally, 6 minus 3 gives me a +3. And so translating this into a system gives me what?
Y equals 3 and x equals 3 and y equals -2.
There we go. Y equals -2. And then we could check it. It's an odd problem, so we should check in the back of the book and be like, oh, yep, that's right. Or if it's not, it'd be really good to go, okay, plug in my 3, plug in my -2 and check them. Yeah, the first one works. I'm not going to worry about the second one, but yeah, so that's what, so a few key things here to keep in mind. And this is, I'm saying this because I saw this a lot. And I know that I said in class, like, sometimes you notice you could just do this and that, and that's cool. And maybe I didn't stress enough that at this point right now, we're not going to skip steps. And we are going to do this exactly every single time. And if you're doing it right, if you're following these steps, then in every single case, you're going to end up with a leading 1. And that should be like your first real step, besides just translating this. So I guess step 2, like you're getting a leading 1. And that leading 1 is going to stay there the entire time. That's not going to change. For the rest of every matrix, for every matrix that you write thereafter, that 1 is going to be in that spot. Ditto with the second leading 1. Once you get it, every single matrix that you write afterwards is going to have it in there. And again, like sometimes you notice, hey, man, if I just multiply this one by this number, then I could cancel this out really easily. And like, yeah, that's great. And in this specific case, that works. But in general, right? And this is what we're trying to do is, in general, this is always going to occur. You're going to get a leading 1 in the top left, and it's going to stay there until the very end. And then after you've done, and then after this, you're going to get zeros beneath it, which are going to stay there every single time. Then you're going to move over and get a new leading 1. And that leading 1 is going to stay there for every single point. And then as you go along, you're going to get zeros moving above it, which when we move to 3x3s, it's going to be the same thing. You're going to get a leading 1 in the top left, and then you're going to get a bunch of zeros below it. Then the next one's going to come up along. You're going to get a 1, and it's going to stay 1 every single time as the zeros start to build up beneath it. And then so on and so on. And then we're going to start the back solving part, right? Where you get your zeros above and everything. But in every case, no matter how big or small the matrix is, this is what you're going to see. You're going to start with a 1 that's going to persist forever. Then at some point, you get a 1 that shows up here, and it persists forever. And so on down the line. Once you have a leading 1, it stays there. Yeah, that's the algorithm. That's how it works. Like this set of instructions will, if they're followed exactly, that's always going to occur. There's no way around that. There's never a point where you say multiply by 5 and then it just stays up there and it becomes 5 now. Like that's not part of the algorithm. So, yeah. We have some time. We should do one more. We should do one more real quick. So let's do one from here. All right. Any questions on writing this next stuff up? Cool. So here's a system. 4x plus y equals 1. X minus 2y equals 16. Now, one thing I said is one of the freedoms that you have in this algorithm, as we're doing it right now, there's a lot of freedom to be had later. But for right now, one of the freedoms you have is If you notice that one of those rows has a leading one, go ahead and make it your top row. And in this case, I could see that that bottom row is 1, -2, 16. Why don't I just go ahead and write it that way? 1, -2, 16 will be my top row. And then 4, 1, 1 is my bottom row. Now, okay, we have a leading one. Okay, good. Step 2 is done. So now we need to get zeros underneath it. And I ask myself, oh, man,
Times the top by -4 and plus it to the bottom.
there we go. So -4 is what I'm going to multiply that through. Gives me -4 plus 8. 16 and 4. Is that 64? I think it is. 2, 4, 5, 6, 64. Well,
-64, right?
ooh, good catch. Gold star. You get a gold star and a smiley face. Excellent. 1, -2, 16. The top row is not changing in this case. I can only change one row at a time. So the 4 and the 4 give me a 0, just like we want. 1 and the 8 give me a 9. 1 and -64 gives me -63. Okay, now what do we do?
Times the bottom by 1/8. 1/9. 1/9.
1/9. There we go. Right. Because we're trying to get a new leading one in this position. And so the only number that's going to turn that thing into a 1 is 1/9. So I'm not changing the top. And so 1 -2, 16, 0. It has to be a 1. That's the whole point. 1/9, 9 is that. Okay. So what's -63 over 9?
5.
Mhm.
-5.
7.
Wait, no, -7.
-7. I have to, do you know this trick? This is a really cool trick with nines. If you have 9 times something, you could go, let's say 9 times 3. You go 1, 2, 3. And over here you have a 2. Over here you have a 7. It's 27. And so 9 times, say, 1, 2, 3, 4, 5, 6, 7, 8. 9 times 8 would be, I have 7 fingers over here, 2 fingers over here. And what I did is I was like, I think 63 is divisible by 9. And so what I did, I was like, well, 6 would be here, 3 would be there. Oh yeah, and so 1, 2, 3, 4, 5, 6, 7. 9 times 7 is 63. That's how I do it. My 9, that's the only way I know my nines. I have not memorized nines. I use my fingers. So -7. There we go. So -7 right there. Now, okay, we are done with getting a new leading one. And so we need to get zeros above the new leading one.
If you times the bottom by 2 and plus it to the top.
There we go. Times by 2 and then plus the top. So multiplying through by 2, we get 0, 2, -14. And that's what we're adding. Now, one more thing. We are not changing the bottom, so I'm writing the bottom exactly. Now we add that to that. The 0 and the 1, oh, lo and behold, that leading one is not changing. 2 and -2 give me a 0, which is exactly what we wanted. And then what's 16 minus 14?
-2.
+2.
2.
Yep. And so, okay, I think. Okay, let's translate this back into systems. So the system, this means, what's that top row mean?
X equals 2.
X is 2 and Y is 7.
There we go.
Wait, wouldn't it be -7?
Yeah.
Oh boy, you both get gold stars and smiley faces. Thank you. Yeah, good job. So there we go. -7. Good catch. Thank you. Excellent. I'm impressed. You guys are knocking this out. Like that's the thing. Like I said, and I keep saying, right, is sometimes in certain cases it's so obvious. And you're like, why can't I just do this, right? I know that 400 divided by 25 is 16. It's obvious. It's like, yeah, I know. And this is really the part of all of this that I hate, is saying, nope, you got to do it this way. Because at the same time, then in class, I say, there are infinitely many ways to solve a math problem. And it's like, yeah, and that's true. But the point of this, again, is not to get to the right answer. And it's not really, even in this case, to learn the concept any deeper. It's that this method, this algorithm for doing this, is so powerful and so useful. And it takes so much guesswork out of things, just like long division, right? Division is a very hard thing. Like it is. In fact, I'm not sure if you guys know about cryptography, something called public key cryptography. And it's like what the NSA and the CIA use to send messages and stuff. And it's all based on the fact that division is very hard. Division is a ridiculously hard thing to do, like even for computers. And it's like, but it's really nice to have a long division algorithm that takes the guesswork out of it. And so this is, in the same way, solving systems of linear equations like this is a very hard thing. And every now and then you get lucky and you go, hey, dude, I could just like add those together to start off with, and I cancel out one of my things. It's like, yeah, but that's not always going to be the case. Like oftentimes, in fact, most always, the system that you end up with, there aren't any tricks. And you can't notice like, oh, hey, look at that. I could just add those together. If I subtract the top from the bottom, I can make my life a lot easier. And since that's the case, we're going to really, really, really drive home this algorithm. And then once you get that down, then when you notice those little tricks and stuff, absolutely, I'll be happy if you use them. But at this point, we're trying to drive home this algorithm. Does that make sense? Am I being unreasonable by asking for that? So if there are no questions, we are 3 minutes over time. So if there are no other questions or anything like that, we're good to go.